Let's take a big picture view of integration now. We might ask, do all reasonable functions have antiderivatives? I say reasonable here because in upper levels of math, people have defined all kinds of crazy functions that exist only at certain, like an infinite dust of points, which we're not going to worry about. So do you think all reasonable functions have antiderivatives? What does it mean to be reasonable? Well, you might say, do all continuous functions have antiderivatives? Continuous, there are reasonable non-continuous functions like the unit step function, but continuous functions are especially reasonable, right? So we might ask, do all continuous functions have antiderivatives? And it's not even clear what does it mean to have an antiderivative. Does it have an antiderivative formula, something involving e's and signs and stuff? Well, let's think, what does it mean to have a formula? There's a definition called elementary functions, and we don't mean elementary school here. We mean things that you would see in basically algebra and trig classes. And so that's plus, minus, multiply, divide, and powers including roots. And then some of our other favorite stuff like logs, e to the x, trig, inverse trig, hyperbolic trig. Although we saw in the other video that hyperbolic trig is really just e to the x in other forms, right? Inverse hyperbolic trig, which you might imagine involves logs of stuff, it does. So all those are considered elementary functions, and then any finite combination of these, like adding and then multiplying and then taking a log and stuff. Why am I saying finite there? Well, it turns out some infinite sums can give you stuff that you wouldn't call an elementary function. And do we really want to deal with infinite sums and call them elementary? Not really. We'll deal with infinite sums in a later chapter. So now that we've talked about elementary functions, let's ask about derivatives. Does every elementary function have a derivative that is expressible in terms of elementary functions? And the answer is yes. That's kind of what we mean by these nice functions, right? And how do you get that derivative function? You can just apply rules mechanically. Chain rule, product rule, quotient rule, constant multiple rule. So we can just say mechanical application of derivative rules. Product rule, quotient, chain rule. Will work, that there's no creativity required. But what about, does every elementary function have an antiderivative that is elementary? Well, it turns out the answer is no. And the big important one is e to the negative x squared. which looks like a bell curve, or it is basically the statistical bell curve. The statistical bell curve, we put a divide by 2 and throw a constant out front, but the shape is the same. What about the integral of e to the negative x squared dx? What does that look like? Well, we can think in terms of cumulative area so far. Like over here, I'm not adding very much area, so it's going to be fairly flat. And then by the time I get over here, I'm adding more and more area. And then by the time I get over here, I'm not adding very much more area anymore. So I get something like that. So it looks like 1 over 1 plus e to the minus x, but not exactly. So does it have an antiderivative? Yes, you could say this set of points in the plane, if you take the derivative of that, you get this. But is there a formula for it? Not exactly. There's something that gets you close. I mean, you could say this is a formula for it, but that's not really going to tell you how to do it on a calculator, right? And it's not just that no one has managed to find one yet. People have proved that there is no elementary function for that antiderivative. There's other similar functions like sine x over x. There's no antiderivative of that. There's no antiderivative formula that's nice. Integral of sine e to the x, integral of sine x squared, integral of root 1 plus x to the fourth. So that means that the arc length of a cubic, how would you take arc length? Remember, f prime of a cubic would be something x squared, then square that, you get x to the fourth. So there's no nice formula for arc length of a cubic. So all of these are related to, or types of what are called, let me spell it right, special functions. And I have something in the big file of homework that talks about some of the special functions and what they're used for. All right, so the big picture is that not every elementary function has an elementary antiderivative formula, although the antiderivative still exists as kind of an abstract function that you could approximate. There are useful functions that are like that. As we've seen, taking antiderivatives requires some creativity. You might try U substitution, try integration by parts, try trig substitution, try partial fractions. So that'll be the next thing we talk about.